Hey everyone, welcome back to the Deep Dive. Talk Tensors here, ready to break down another fascinating paper from the world of machine learning. You know the drill, right? We take these dense academic papers and we try to distill the key takeaways, the aha moments, all the good stuff.
Exactly. No need to wade through all that jargon and technical complexity. We do the heavy lifting so you can stay ahead of the curve, understand what's really important and why it matters.
And today we're diving deep into a paper that tackles a question at the forefront of AI research: how to accurately measure the intelligence of these increasingly sophisticated AI agents, especially those driven by LLMs.
LLMs, those large language models, are showing some really remarkable abilities these days, right? They're understanding and generating text, they're even writing code, and they're getting really good at reasoning, planning, and solving problems.
Yeah, particularly in those well-defined, predictable scenarios, the kind we often refer to as closed world environments, where the rules are clear and the possibilities are somewhat limited.
Right, but the real test, and where this paper makes a big contribution, is in evaluating LLMs in those more complex, unpredictable open world situations like you might find in strategic games.
Imagine a game like chess, or a really complex strategy video game. It's not just about knowing the rules, it's about understanding your opponent's motivations, trying to predict their moves, and dealing with risk and uncertainty.
Absolutely. And this paper argues that to truly understand how intelligent these AI agents are becoming, we need to test them in these more challenging environments. And that's where their new benchmark, DSGBench, comes in.
Okay, DSGBench. That's the heart of this paper. So what exactly is it? What makes it so unique, so important?
Well, the interesting thing about DSGBench is it's built around this multi-game environment. So it doesn't just focus on one game or one type of game, but it uses several different games that support different kinds of interactions, both turn-based, where you're taking turns with your opponent, and real-time, where actions are happening simultaneously.
So right away, it sounds like this could give us a much broader, richer picture of an AI agent's capabilities than a benchmark that's only looking at performance in a single game.
Right. And on top of that, DSGBench incorporates what they call fine-grained capability metrics. Think of it like this. Instead of just saying, oh, this AI agent is good at playing this game, these metrics look at the specific skills that contribute to that success.
So it's kind of like, instead of just saying a chef is good, you're looking at their knife skills, their ability to create different sauces, their baking skills, and breaking it down into these individual components.
Precisely. DSGBench breaks down gameplay into those essential cognitive skills like strategic planning, real-time decision-making, even collaboration if it's a team-based game.
Yeah.
It really tries to dissect the AI's intelligence.
That makes a lot of sense. Knowing the final score only tells you so much, right? You need to understand how the AI got there, what decisions it made along the way.
Exactly. And to really understand that how, DSGBench includes these cool tools for decision trajectory tracking. It's like having a replay of the AI's thought process, so you can see the sequence of decisions it made throughout the game.
So you can rewind, see what the AI chose to do at each critical juncture, and try to figure out why it made those choices.
Exactly. It lets us peer into the black box, so to speak. So throughout the gameplay, the framework is evaluating the LLM-based agent by having it observe the game, presenting it with a prompt based on what it sees, and then translating the AI's response into an action in the game. And it's doing this constantly in this loop as the game plays out.
So the authors of this paper argue that DSGBench addresses some big shortcomings in how we currently evaluate AI. What are some of those limitations they're pointing out?
Well, they point out that a lot of existing benchmarks are kind of narrow in focus. They might test one very specific capability in isolation, or they might rely on static data sets that don't really reflect the dynamic nature of the real world, or in this case, a strategic game.
So it's like an existing benchmark might be able to tell you if an AI can plan one move effectively, but it can't tell you how that AI would integrate that move into a larger strategy, especially when it has to react to what its opponent is doing.
Exactly. They specifically mention benchmarks like Agent Bench and GameBench, which often just focus on the final outcome, like did the AI win or lose? And while that's important, it doesn't give you that deep understanding of the reasoning that went into those decisions.
So DSGBench aims to give us that deeper picture. The outline mentions a table that compares DSGBench to several other benchmarks. What's the main takeaway from that comparison?
Yeah, Table 1 in the paper really highlights how DSGBench is trying to be more holistic in its approach. Some benchmarks might be really good at one or two things, like maybe really deep game theory analysis, or they're great at real-time interactions. But DSGBench tries to bring together a lot of different elements like complex game theory, fine-grained metrics, decision trajectory analysis, and it's doing this across a diverse range of game scenarios.
So it's like they're saying, we want to measure all these different aspects of intelligence in a coordinated way. Why is this so important now? Why do we need this kind of comprehensive evaluation?
Because the capabilities of these LLMs are growing so rapidly, we can't just be satisfied with knowing if they can achieve a goal. We need to understand how they're getting there, especially when you factor in incomplete information, uncertainty, and the fact that they're often playing against other intelligent agents, whether it's humans or other AI.
So DSGBench is this new comprehensive framework, but what's the backstory here? What led to its creation? What were some of the key trends that made it necessary?
Well, to understand that, you have to look at the evolution of how we evaluate AI. We've moved from testing on static data sets like image recognition or reading comprehension to evaluating them in these more dynamic, interactive environments, especially games.
Right, because a static data set can't really tell you how an AI will react when it's interacting with a changing environment, a world where its actions have consequences.
Exactly. Researchers realized that to really test things like generating novel content, engaging in multi-turn conversations, and playing complex roles, they needed environments where the AI has to think on its feet, adapt to the actions of others.
And we're seeing LLMs being applied to a wider and wider range of these interactive settings, right? Like software development, robotics, even simulations of societies and policymaking.
Yeah, and within all those areas, strategy games have really emerged as these ideal platforms for testing high-level decision-making in LLMs.
Because they require that ability to think multiple steps ahead, to predict what your opponent might do, and to balance competing objectives in the face of uncertainty.
Right. And they often force you to think about long-term consequences, which of course has a lot of parallels to real-world decision-making. And as research has progressed, we've discovered that LLMs are capable of some surprisingly advanced cognitive abilities. Some of them exhibit what looks like chain of thought reasoning, like humans. Some can build internal models of the world around them. There's even some evidence to suggest they have a rudimentary theory of mind.
It's fascinating to think that an AI could be trying to anticipate what a human player, or even another AI, is thinking and planning in a complex strategic game.
Right. It gets to the heart of what we think of as intelligence, and that's why DSGBench is so important. It provides this framework for really dissecting those advanced cognitive abilities in these challenging environments.
So let's dive into the technical side of DSGBench a bit. The paper describes how the agent interacts with the environment using something called a partially observable Markov decision process. That sounds pretty technical. Can you break that down for us?
Sure. So a POMDP is a way to formally describe how an agent, like our AI, makes decisions when it doesn't have all the information. Imagine you're playing a game and you can only see part of the board. That's the partially observable part.
Makes sense.
So DSGBench defines the key elements of this process. First, you have W, which is the victory condition. What's the AI trying to achieve? Is it capturing the opponent's base? Is it getting a certain score? That's the goal.
Got it. What's next?
Then there's S, the state space, which is every possible configuration of the game world. Imagine all the different ways the pieces could be arranged on a chessboard. Then you have A, the action space, which is all the legal moves the AI can make.
So every possible move it's allowed to take.
Right. And then there's O, the observation space. This is what the AI can actually perceive about the game at any given time. And remember, it's partially observable, so it might not know everything that's going on. And finally, you have T, the state transition function, which is how the game world changes from one state to the next based on the AI's actions and maybe some other things happening in the game.
Okay, so it's essentially trying to capture the fact that in a strategic game, you don't always have perfect information and have to make decisions based on what you can see.
Exactly. And the outline also mentions DSGBench looks at two levels of inference. So in simpler games, like turn-based ones with clearly defined states, it looks at single-level inference where the AI is basically just making decisions based on what it can observe directly. But in more complex games, like real-time strategy games with tons of information, it uses two-level inference. This means it considers both high-level strategic planning, like managing resources and deciding what units to build, and also low-level tactical decisions, like how individual units should move and fight in the moment.
So you can't just have a grand strategy in StarCraft, for instance. You also have to be able to control your units effectively on the battlefield. Now, how does DSGBench actually calculate these capability scores for the AI agents?
It takes into account how the AI performs across multiple games, looking at a specific cognitive dimension, like strategic planning or real-time decision-making. It basically combines all these different performance metrics into a single score that reflects how well the AI did on that particular skill.
So it's like creating a standardized measure of intelligence for that specific dimension. And I see here that the outline mentions a 5-dimensional assessment system based on human cognitive theories. What are those 5 dimensions?
So drawing from theories like dual systems cognitive theory, distributed cognition theory, and dynamic decision theory, they came up with 5 core dimensions for evaluating the AI agents.
They are
Strategic planning, so the ability to make long-term plans, real-time decision-making, making good choices quickly under pressure, social reasoning, understanding and interacting with other agents, maybe even deceiving them, team collaboration, working together effectively with teammates, and adaptive learning, improving over time based on experience and feedback.
Wow, that covers a lot of ground. And each of the games in DSGBench is specifically chosen to test these different capabilities, right?
Absolutely. For example, StarCraft II and Civilization are really good for evaluating strategic planning and real-time decision-making because they're so complex and fast-paced. Games like Diplomacy and Werewolf are great for social reasoning and team collaboration because they're all about interacting with other players, forming alliances, understanding their motivations. And many of the games, including StarCraft II, Civilization, and Stratego, can give insights into adaptive learning by seeing how the AI improves over multiple games.
So the choice of games is very deliberate, designed to really push the AI agents to their limits. Earlier, you mentioned these fine-grained capability metrics. Can you give a concrete example of what that looks like?
Sure. Let's take strategic planning in StarCraft II. DSGBench doesn't just measure wins and losses. It looks at things like how efficiently the AI gathers resources, how well it manages its supply lines, how quickly it builds up its army, those kinds of things.
So even if 2 AI agents both win, one might be considered better at strategic planning because it did a more efficient job of building its economy and producing units throughout the game.
Exactly. And to really drill down into the decision-making process, they use that decision trajectory tracking system. It basically records every action the AI takes, the context in which it took that action, and the immediate outcomes of that action.
So it's like having a detailed log of the AI's thought process, so you can see exactly why it made each decision. And then there's the implementation side of DSGBench. The outline mentions it uses different software modules. What can you tell us about that?
So to make the evaluation process automated and consistent, they built DSGBench with several modules. There's the game manager, which runs the whole evaluation, the data collector, which handles all the game and agent data, the GameM, which connects the AI to the actual game environment, and the history tracker, which keeps track of all the decisions or outcomes.
Okay, that gives us a good overview of the framework itself. Now, what did the researchers find when they used DSGBench to evaluate some of the leading LLMs?
They tested 6 different LLMs, a mix of commercial models like GPT-4o, GPT 3.5 Turbo, and Gemini 1.5 Flash, and open source models like DeepSeek v2.5, and some from the Llama 3 family.
A good mix to represent what's out there. What were the key findings?
The quantitative results, which you can find in Table 6 of the paper, showed some really interesting patterns. Some models were better at certain cognitive dimensions. For example, Gemini 1.5 Flash seemed to excel at strategic planning and adaptive learning, while GPT-4o was really good at social reasoning tasks. Generally, there was a bit of a performance gap between the commercial and open source models, especially in strategic planning.
So not too surprisingly, the models with more resources behind them tended to do a bit better overall.
Right. But it's not a simple story. The open source models were surprisingly competitive in some areas, like real-time decision-making in StarCraft II. And the results also suggest that different LLM architectures might be better suited for different kinds of tasks.
It's not one size fits all. So beyond the raw numbers, what did they learn from actually watching these AI agents play these games?
The qualitative analysis in Section 5.3 of the paper gives us some great insights. In those structured, turn-based games, the commercial models seemed better at sticking to their long-term plans. For example, GPT-4o showed a real knack for understanding how to prioritize resources and make coherent foreign policy decisions in Civilization. But even the best models sometimes struggled to adapt when something unexpected happened.
What about the real-time environments like StarCraft 2?
StarCraft 2 really exposed some limitations in what the researchers called temporal reasoning, the ability to make decisions quickly and effectively in a rapidly changing situation. Even GPT 3.5 Turbo, which is a very powerful model, sometimes struggled to keep up with the demands of the game. The open source models generally had an even harder time in that environment.
So even for the most advanced LLMs, reacting and adapting in real time remains a big challenge. What about those social reasoning tasks at games like Diplomacy and Werewolf?
Yeah, these were tricky for many of the models. GPT-4o had some success forming alliances in diplomacy, but its performance was a bit inconsistent. The open source models often struggled to understand the social dynamics of these games, giving responses that were either repetitive, off-topic, or just didn't make sense in the context of the social interaction.
So building LLMs that can really understand and participate in those complex, nuanced social situations is still a work in progress. And how did that decision trajectory tracking analysis help them interpret the results?
By analyzing the step-by-step progression of the games, they could see how the LLM's decisions evolved throughout a match. For example, in StarCraft 2, they could track how an LLM adjusted its resource allocation and unit production based on the opponent's actions or changes in the game state. It helps to understand the rationale behind the AI's choices, even when those choices aren't perfect.
It's like seeing the gears turning inside the AI's mind. Now, the paper also has a section called Novel Notions and Future Research. What are some of the key directions they point to for future work in this area?
They suggest two really interesting directions. The first is creating a massive unified data set of game trajectories from all these strategy games. Imagine having a huge repository of detailed gameplay data that researchers could use to train and test new AI agents.
That would be a huge resource for the whole field.
Right. And the second direction is developing a specialized reasoning framework for multi-strategy games. They want to create AI agents that can better integrate all those different cognitive skills that are needed for strategic gameplay.
So it's about not just evaluating, but also improving the way these AI agents think and learn in these challenging environments.
Absolutely. And ultimately, they hope this will lead to the development of AI systems that are not just intelligent, but also more adaptable, more robust, more able to handle the kinds of complex, open-ended challenges that we face in the real world.
Well, that was a fascinating deep dive into the world of evaluating AI, specifically these LLM-based agents, and how they perform in these complex strategic environments. DSGBench is clearly a really important contribution to the field, giving researchers a much more detailed and nuanced understanding of how these AI systems are thinking and making decisions.
It's a great example of how we're constantly pushing the boundaries of what AI can do, and also how we're developing new tools to understand and evaluate those capabilities.
And for you, our listeners, we hope this deep dive has given you some food for thought. As these AI systems become more and more sophisticated, how do we measure their intelligence? How do we ensure that they're making decisions in a way that's aligned with our values and goals?
These are big questions, and DSGBench is just one step in a long journey. But it's an important step, and it raises a lot of really interesting questions for the future of AI.
We'd love to hear your thoughts on all of this. Feel free to reach out and share your perspective on evaluating AI and what role you think LLMs will play in our increasingly complex world.
And join us next time on the Deep Dive, where we'll be...
Well, you'll just have to tune in to find out.
Until then, keep exploring, keep learning, and keep asking those big questions about the future of AI. Thanks for listening.